for me as well, and go ahead with my talk. So, first of all, what we do here as engineers always, it says that we have a state of our system, and this state describes the entire system behavior. And we always assume that it is based on the Markov property. So since we have the state that fully defines how the system functions, we're not dependent on any previous time steps. That's like if you have the whole state of the universe, then nothing will depend on the past. So, and for those that are not that familiar, we start off with some prior knowledge that has to come from somewhere, that could be a point for criticism, which is always if you have frequentist versus Bayesian estimation, it's always there, that prior probability that it comes in here. And then we do our first update step. And this update step is based on Bayes formula, and I've written it here in the alternative form, in which I use the law of total probability in the denominator. And it is essentially our posterior density is equal to the likelihood for z, so the actual measurement that we have, conditioned on the state. Generally, this does not need to be a density at all, and especially if we consider different domains, that z can be on just any domain, but it still is a function of x, and x shall be, in our case, for example, from periodic domain. So, and multiply it with the prior density, and then you have just the integral over that. So, and that's also called the normalization constant. And since normalization can be easy depending on what you do, this is also commonly written that it's just proportional to likelihood times prior. I think everybody's familiar with that. Then what's actually special is that we have a prediction step. This prediction step gives you the opportunity to describe the state at the next time step based on your current knowledge. This can be written as a so-called transition density that gives you the probability density at state xt plus 1 based on xt. And what we then do is to just get our knowledge, our predicted knowledge of the next time step, is that we multiply this with our posterior density of the update step, and then we marginalize it out. I mean, if you just imagine that that's a joint density in here, and we marginalize this out. Okay, then, and this is just some notation we engineers do. I'm not sure if you're familiar with that. And we say that here is a unit delay, and that's just to close the loop to say that, okay, now we can do it like that over and over again. And here we go from t plus 1 to t. Good. Then classical recursive Bayesian estimators are the Kalman filter. And if you have a prior density with, for example, its mean at 60 degrees and you have likelihood with a mean at 300 degrees, and you would apply just naively a Kalman filter, which is what you do on Euclidean domains commonly, then the result of the Kalman filter would have its mean at 180 degrees. And for all of us that are from doing circular estimation, we know that this is very stupid. But it's not really a problem of Bayes formula. Bayes formula, if you apply it correctly, then you have this result. And I would say that this is our 2-rep normal, and you see there's a small tiny mode here, all stuff like that is totally not considered by a Kalman filter. And what I should say here is a word of caution. If I had shifted this whole thing differently, then this would have looked better. And the first strategy you can have here to make Kalman filtering work is to shift your boundary of periodicity in a way that it works better. And this makes it much better, but it does not really capture everything that we have in circular and directional estimation. For example, if we had a measurement, if a per density and the likelihood were completely contradictory, you would have one at 0 and one at pi, and they would have the same concentration value, for example, in different mesons, then what you would get out is a circular normal. You would have like a circular uniform. You would have just uniform on the whole circle, and the Kalman filter would never give you that, because the Kalman filter is always saying that my probability mass is getting more and more concentrated the more measurements I have, although in directional estimation measurements can give you more uncertainty. So, and manifolds that I've considered here are the circle. I've done it for the hypertorus. I've done it for the hypersphere. I've done it for the hyperhemisphere. I also count this as periodic because this is 4 unit quaternions. So if you go at one side, you come out the other here. So it's not as clear that this is a periodic manifold, but this is interpreted to be a periodic manifold. But indeed, that's actually not necessary. The grid-based method that I'm presenting here, they can be used for the hyperrectangle if you just think the hyperrectangle is an unwrapped torus, and then you see that this is closely related. It could be improved by really having the borders then of the entire hyperrectangle, but it's still, you can still use it and you only have some differences in the edges. What I've not yet done, but what is also possible, obviously, is that you could do the hyperball or polydes, like Cartesian products of disks. Okay, now if we go about a grid-based representation, then we have to think about, well, what do our grid points mean, and what do the corresponding grid values for each grid point? I will call them beta. We've got a grid value which I call gamma. Well, you could say that this is the probability mass in a region. You say that the domain is partitioned and each of the grid value corresponds to a probability mass. The second interpretation, which I'll focus on, is that this is the function value of a continuous density at a certain point. And depending on the manifold, this can be where you place your grids can be different. Like an easy thing is, by the way, is to use the equiangular grid, where you have the azimuth and elevation angle. You subdivide them in some way, but what you get then is you have it much more dense towards the poles. And here I've got an equal area partitioning grid like that, where you put them in a way that they have a region around them that is of equal area for all of them. So, but then now we've got some functional values. Now the question is regarding an interpolation. And if we now unwrap our torus, show it here, and just the hyperhemisphere, I'm just always throwing in some of the manifolds because it's applicable to all of them. So I want to have a bit of a mix in here. Then the easiest interpolation is just to have a nearest neighbor. So we've got the function value at a certain point, and then we just search which is the nearest point. And actually, if you have, for example, that torus up there, then you could use modular arithmetics to do it in O of 1. So in just a single operation, or just multiple single operations. And you could do the same for the hyperhemisphere, but this is not really good. This is not making optimal use. So what I'm doing is I related to works which I've done previously, where I did really filter on function basis. I give an interpolation based on function basis. On the torus, for example, this is a multidimensional Fourier series, like trigonometric polynomial. With that I mean exponential functions. And for the hyperhemisphere, I use spherical harmonics. And really, the interpolation, it looks so close to the original density that I have not shown the original density, because you could not visually distinguish that from one another. And in the next slide, we go to something that maybe I teased it a bit when I gave a comment on one of the previous presentations. Well, for the smooth interpolation, if you just go on like that, I'm having it here for the sphere. If you take your vector of grid values, you do a spherical harmonics transform, and you have a matrix of spherical harmonics coefficients, then, well, you have that series. It's truncated, obviously, so just this finite sum. And since you do that approximation, you could get function values that are negative. So what we can do instead is that we take the square root of these grid values and then do a spherical harmonics transform, have our function here, and then square all of them, and then we have successfully ensured that this is non-negative everywhere. You could think of other things that, for example, the taking logarithm and exponent, and actually that's also quite an interesting transformation, because you could have then could very easily operate with generalized Hermesis, but what you would always have to consider, we need both the prediction and the update step, and in this case you wouldn't have both of them easily. So this is then our interpolation, which looks pretty good and is definitely guaranteed to only have non-negative function values. But what have we used here? We have used that all the grid values are non-negative. And that's something that we will then note, that both the prediction and update step that I'm presenting both ensure this. So if we have Bayes formula to implement, then we have the vector of function values of our prior density, which then, if you interpolate it, looks like that. And we've got that of our likelihood. And then all we need to do is just multiply them, each of the values. And if you multiply two non-negative numbers, then obviously this is always non-negative. And the nice thing is that actually you're proportional to the true function values of the posterior density. But if you have some increase in the complexity of your function, this goes to if you multiply two Fourier series, you may get, or trigonometric polynomials, then you get coefficients for terms of even higher order than you had before. So your multiplication result could get you, for example, another mode somewhere where there wasn't one previously, even between two of the grid points, if you think of the grid points. And that is an approximation error you do. But the good thing is that your approximation error never causes negative function values. And this is a bit of a contrast to when I was directly filtering on the domain of the Fourier series, for example. Then I had to do some extra steps to really make this work, because there this had more of a characteristic of a low pass filter, the approximation I did there. And here it's just like for the engineers who know that aliasing, it's like we deliberately accept aliasing. But by doing so, we always have the non-negative function values, and we have a totally different characteristics than the other filter, which I did for Fourier series, where you had a deliberate low pass filtering. So you have these frequencies with very, very high, just really eradicated. Good. Then the Chapman-Kolmogorov equation, as I said, we have here the transition density multiplied with posterior and then marginalized out. How do we do that? We take the posterior that we get and start off with here, and here's our transition density visualized as a two-dimensional function, just saying that xt plus 1 xt. And now if we interpret this density that we start off with as a two-dimensional function by just saying, well, it's constant in this other dimension, then how this term, this joint density looks like is just a multiplication. How we could realize is that we could expand this vector. We just repeat it one after another, just do a matrix full of these identical vectors and then do a pointwise product. So we just do a multiplication, as in the case of the base formula. And then we get this density. And yeah, this density, it's based on this nonlinear thing, and you can get very, very well also skewed ones with all these, because this is based on a trigonometric polynomial. Again, this interpolation, having skewed densities here is obviously no problem. So the last step we have to do is marginalize this out. And for this, we just say we use rectangle rule for integration. And this means that we just take one of the vectors out of the matrix and then we normalize it appropriately. And then we've got our prediction result. Good. Now, to do this on the sphere, it's a bit more complicated there than to visualize how a transition density looks like on the sphere. Then here you have the state xt, and then I visualize that as thus that I say here I assume this one is the current xt, and then I give you the transition density for xt plus 1 based on that point. So, and there you see you have something. And you really need the full Chapman-Kolmogorov equation if you have a behavior like that, where how it behaves on the sphere is actually dependent on where you are in the sphere. If it's not dependent and you have some noise that is rotationally symmetric, then you could use one of the convolution approaches from literature. If it's not like that, then you don't have, because in that case, you can really have some form of convolution, which is not really uniquely defined, or in the other case, there are some other definitions, but we do not need all of these definitions if we really use Chapman-Kolmogorov as it is. Then how do we then do it? Again, we go rectangle rule. We have the area of our patch size that we consider, and then we just have the function value of the joint density there, and that is the transition density at that point at which we want to evaluate it on, given that we're considering the first grid point, the second grid point, the third grid point, and really all of these grid points. And yes, then we have successfully marginalized out this from the joint density, and then we have got one of the new grid values. And if you rewrite this, because we know what the transition density at beta I given that beta j is, then this is just a sum multiplied here with the patch size due to the integration rule. And then we have certain entries of the transition density of that matrix, and here of that other vector. And the nice thing is that if you want to have all grid values simultaneously, this is just a scaled matrix vector product. So now we are also able to really solve this reasonably efficiently. And we always ensure the non-negativity here, because we're just multiplying non-negative values, we're adding non-negative values, and we divide it by a positive constant. So, and I've done several evaluations against other filters that are there that have been derived similar to the Kalman filter. For example, the von Mises-Fischer filter is taking the ideas of the Kalman filter, but taking it to the sphere in the term of the von Mises-Fischer distribution. And actually, if you consider the sphere here, I've not filtered out any experiment. When I do an experiment, I also show the result, even if they are not like good for me. So, and here you see the von Mises-Fischer distribution. It takes me quite a couple of grid points to really match its performance, and the von Mises-Fischer filter is also very highly performant. So in this easy scenario, you could just use the von Mises-Fischer filter. Then I've considered a scenario on the hyperhemisphere. What I use as an alternative is the Bingham filter. And I did this because I say this hyperhemisphere could also be considered as an entire sphere. And then you just take something that's antipodally symmetric. So this Bingham filter, it also takes me a couple of coefficients to really catch up with that Bingham filter, but the Bingham filter with its normalization constant is actually slower, because what I do, it's just vector products and matrix vector products. It's nothing more. For a computer, this is highly performance stuff we're doing. It's only highly optimized operations that we can use. And all of this is done in MATLAB. So I didn't cheat that I just implemented one of them in C++ and one of them in MATLAB. No, this is both in MATLAB. And then for the torus, I did a comparison with the Fourier filters that I've mentioned previously. And actually, the performance is pretty much similar. But the good thing is with the grid approach, as I said previously, you do not have to worry about something getting negative values there. So there is a bit of a theoretical advantage. But I want to say that the Fourier filters can be beneficial if you have some sort of density where you can have closed form solutions for trigonometric moments, which do exist for some of them. And then you can have more efficient approximation there and also more accurate. So let's get to my summary. This is a quite versatile filtering scheme that you can apply to periodic domains and also bounded. That's actually where it really has its origin, grid filtering. It's also known as the name histogram filtering. That's a histogram in 1D. And I told you how you can get a non-negative interpolation to have a really smooth and nice density out of it. And in all of the scenarios, which I didn't mention that explicitly, the particle filter is always much slower. So what could be further steps? Adaptive grids. Kyle already mentioned adaptive grids for hyperspherical manifolds. You could also do that for other manifolds and consider other types of adaptive grids, because placing more grid points where there is more probability mass is a bit more efficient, or can be even more highly more efficient depending on how it is distributed. And then also consider Cartesian products of bounded and Euclidean domains. I would do this by saying that on the linear domain, I do some Kalman filtering, and on the other one, I do some grid filtering. And then I do it by splitting up this joint density into one regular density and one conditional density. This is also known as Rao-Black realization in particle filtering. Okay, then this is it for me. Thank you for your attention. I'll be happy to take your questions.
Thank you very much, Florian. And indeed, we have now room for questions for Florian about his talk.
Hello, John Kent here. Very
Hi.
nice talk. I wonder if it's worth trying to classify problems. The very simplest problems would be those that are nice enough that a standard Kalman filter would tend to work. And then you get slightly messier problems, maybe where the grid approach is going to work, and maybe you might even have really messy problems where you might have to go to a particle filter. Would it make sense to divide up problems like this?
Oh, well, sure, there is some. It's not. The problem is sometimes you don't know ahead what really comes up there. But definitely, if you have something that is, for example, you do not really have a continuous domain, but you rather have a discrete domain. So really, it can only come up at some points. For this, I would recommend really using a particle filter, not a grid filter, maybe. For Kalman filtering, yes, you can stick with the standard Kalman filter if your uncertainty is really concentrated, because what we have in our periodic manifolds is that they are locally Euclidean. If you zoom in enough, they look like an Euclidean space. And if this is really the case, that everything, that your whole uncertainty or your whole probability mass is in a really narrowly concentrated region, then you could just put some Kalman filter there.
I think that's exactly my point. If the problem is concentrated enough then you can get away without thinking too hard about the manifold features of the problem. And whilst at a meeting like this, it's great fun to focus on the manifold features, if you want to sell your ideas to a very practically minded engineer, and if his problem is very concentrated in a small region, he might say, why do I need to go to this extra trouble?
Well, sure, he may be right with that, actually. That's actually the reason why some stuff is working. I mean, they have been some drone orientation localization stuff that does not use directional because, well, and if you are having planes have been tracked for like so many years now, and they have these really, really expensive equipment. And if you take that really, really expensive equipment, then you get, well, then you can do almost anything and it will still work. And yeah, so as you say that, to really sell this, it has to be somewhere where it's really not that concentrated. So maybe really, really, really cheap sensors, I would say.
Good.
Thanks.
Okay.
Hello there. I don't know whether.
Yeah, Valdi.
Can you hear me?
Yes.
Yes.
Yeah, because now I'm working on iPad rather than PC because PC is occupied. Very much enjoyed. I think all this on manifold, very eye opener. Simple question, when you do this on sphere, let us take longitude and latitude. You have got theta phi.
Yeah.
So you discretize, and then is theta phi near pole, anything different happens, singularity in your conditional distributions, or doesn't?
Well, these conditional distributions. Okay, there's someone. I will have to mute him. So actually, we've got this density like that. I mean, if you try to have something that maps between a torus and a sphere, then we would have really some singularities there. Absolutely. But if we directly define on the sphere, then we would have, that's probably the point you want to get in, and we could have multiple grid points in one point, which we would have to then reduce one. But actually, that you have to pay attention to, yeah. But that I don't really use that grid a lot, or I don't use it at all. The only advantage to using a grid like this is that you can easily do a spherical harmonics transform out of that grid. But the downside is that it's really just weirdly concentrated near the poles. So I recommend some other. There's a paper about spherical equal area partitioning that I'm using. And one thing that I would also think would be very good is to use Lloyd's algorithm to get an iterative, very homogeneous coverage.
So a few more questions, sorry if you pardon me.
Go ahead.
So these are all conditional, but as I understand, Kalman filter also depend on where you start from. So the initial position distribution at initial, where you start, you had, you showed me this previously, one picture where you start. So where you start, the marginal distribution, I think has it to have some special properties or doesn't matter?
I hope I get this correctly. The prior density really makes a difference, and if you really put this somewhere, if your prior density has somewhere probability mass 0 where your real state is, you may never ever get somewhere. So this can totally destroy it. That's why you usually take something that has probability mass everywhere, and over time, with each iteration, this prior knowledge will fade out of existence.
Yeah, I can't see myself. I think that's the same thing what you had. I don't know how I'm sitting here. But the last question. So it's nice to see beautiful mathematics, which I like. But application, which is your simple-minded, where one can feel what's going on rather than going through the whole computational power. One can do it on calculating machine. Sorry.
Okay. Yeah, that's a great question. Actually, maybe this goes to this slide. Actually, the easiest applications, I would think, they really go into this combination of real and periodic. For example, here I've got this infinitely extruded cylinder, and actually I've got a prototype working for that already. And what you could do is you could estimate the position, meaning the angle, and the angular velocity of a motor. That is what you could do with the Cartesian product of the circle times the real line. And
Okay.
what I really want to get to is like SA3, where you have the full orientation and the position, and then also add the angular velocity and the velocity in the position, the accelerations, to have like a state comprising the position and the orientation and all speeds and velocities. And maybe if you think about drones, so these flying robots, you could also have some additional sensor information like biases, drifts, and all of that, estimate all of that into one huge vector to have a real good tracker.
Okay, so which is your famous particular application in engineering where it has worked?
Well, I would say really this is with drone tracking, this is where it can really make a difference with cheap sensors. You could also apply it to really, as Kyla showed previously, into car tracking. But car tracking, it's even easier because you're really moving more or less on a plane.
Okay. Yeah, it's wonderful. I think I have to learn all this. I have to see one of your paper, especially where you have got this cross product in a form of spherical harmonics, this conditional distribution. I would love to go deeper into it in my own way. So I have to ask you eventually, you've sent me many papers now.
Yeah.
You are so prolific.
That's great. We can always keep in contact and have a call or something. If you have any questions, I'm always happy to reply to that. And maybe as a shameless plug at this point, we've got the nonlinear estimation toolbox for everybody who's not using R but MATLAB. We really have all of that implemented, so you can just use it. And what I'm thinking, what I will do is that I will also try to include the densities of Christoph and Najmeh into the framework. And then we could see how many, to answer my own questions, how many coefficients would we need to have, like, we could just define some measure L2 distance, for example. How many coefficients would we need to have an L2 distance that's like for most reasonable configurations below 10 to the power of -10 or something like that.
Good, wonderful. Well, thanks again. I think
Thank you.
I will take you up on asking questions and making some perhaps Zoom meeting or
Sure.
whatever it takes. So thanks for the kind offer.
Yeah, thank you. Thank you for being here.
If
Great.
I may, I would like to ask a couple of questions, if there is time for that.
Yeah, Christoph has to decide that. He's session chair.
I'm totally fine. We are well in time.
Okay, thanks. So one first question is, if I understood correctly, you emphasize a lot the fact that you have to ensure non-negative evaluations of the density in those grid points in order to build up a filtering algorithm that makes sense. I did. Yes.
Go ahead.
Correct me if I, because as I say, I'm not very familiar with this topic. But I was wondering on the other part of ensuring that you end up with a proper density, which is having a density that, or an approximation to a density that integrates one. So how is that taken into account, and how do you deal with that issue?
Okay, yeah, for the first thing, actually, the going below 0 is actually something that I had a problem with when I was directly working with trigonometric polynomials. So I was, you're probably aware of Fourier series in the one-dimensional case, and then you truncate it, and then the problem is the moment if you stop somewhere, then obviously you lose something, and if especially if your density is highly concentrated, then you may get something where it would go below 0. And even if you can ensure this in some way, normally then you may get into problems, because in the update step you would always get more coefficients, and at some point you have to truncate again. So that's why I went to the grid filters, because in the grid filters, all of that what I showed, if you see this, if you see that formula, there's nothing that voids the non-negativity. If you go to that formula, nothing voids the non-negativity of the grid values. And then to really get a density out of that is non-negative everywhere, then I use an interpolation in which I really first take the square root of all function values on the grid. Then I interpolate it somehow, some suitable way on the sphere, circle, harmonics, trigonometric polynomials if you're on the hypertorus, and then I square the result afterwards. If there was some negative function value, it's now non-negative because I've just squared it.
Yes.
Does that answer the question?
Yes, but then the question is, how do you ensure that that thing is actually a density that integrates one? I'm not so sure if that's immediate from that.
Yeah, actually, we can, for the Fourier series, I've done a proof how this can be ensured. It may need some other proofs for the spherical harmonics, but if you ever want something that is definitely normalized to 1, you can always say we do a nearest neighbor interpolation, and then you have something that you can integrate via the rectangle rule, and then you're good to go. This can easily be normalized then, as you can see.
Yeah, because the approximation will be like a histogram, no, basically.
Yeah.
It will be stepwise one.
Yeah. So yes, I fully agree that this is non-trivial for the Fourier series, actually, but what I've shown for the circular case, and I strongly believe it holds for any dimension, is that if you normalize this nearest neighbor interpolation, which is really, really easy to normalize, you just sum up the grid values and then divide it by something. This is then your normalization constant, that this actually normalizes also the one based on trigonometric polynomials. In both in the case that you take the square root and in the case that you do not take the square root. I have not proven it for the spherical harmonics case, but I believe it holds there similarly.
Okay. So another question, if I may, is that regarding the scalability of this methodology in higher dimensions, I understand that you're mostly interested on the sphere and torus judging, well, or S3, no, judging from the applications that you mentioned. But since the hyper words appeared there, I started thinking about what happens if you go higher in the dimensions. And there, I mean, is the whole idea of covering the sphere with a grid is not so simple. Well, it's not so simple even for for us too. No? And this is one of these Smale's problems. That
Which problem?
Smale's problem is a list of famous mathematical problems. So one of them is how to place points on the sphere such that they are equally separated among them. And the higher you go in the dimensions, is the harder the problem becomes. No? Because you want to cover the whole sphere also in a meaningful way, and sometimes doing a grid on the polar coordinates is not, well, it's not fine enough because you have this concentration on the north and south poles. So I was wondering if you have some experience in higher dimensions, if you have tried to push these techniques to arbitrary dimensions to see what happens there.
Yeah, that is indeed a weakness, I would say. That for 12-dimensional hyperteory, it gets slow, but you somehow can manage this with with not just few coefficients, with I think 5 on every dimension. But if you have only just 3 on every dimension, and then you get to 20D if you have enough memory. But
yes,
that's really as far as you can get.
Mm-hmm.
Then you need, I think, 64 gigabytes of memory or so should get you until 20. The operations themselves is it really depends. What I've just said is only for the case that you have an easy system model and can do it via convolution. If you have to do it via a matrix, so if that is a really complicated model, then you may actually have to quit at 10-dimensional problems, because then it's not that easy anymore.
Yeah.
But in essence, what you then have is you could consider that in the Fourier series context, and there's actually a bit of an equivalence, that you just have some basic trigonometric trigonometric moments that you have, like only the -1, 0, 1, and then all the Cartesian products, like the trigonometric polynomial of order -1 for the first dimension, 0 for the second dimension, 0 for the third dimension, and all of these combinations. You're basically working with something that corresponds to all of these trigonometric moments, and this become a lot and increases exponentially indeed.
Okay.
So yeah, very good question.
Thanks for your thoughts, and thank you very much for your presentation, which I enjoyed a lot.
Yeah, thanks.
Okay, very good. Is there still one more question? If not, then I would like to thank Florian again for this very nice and comment triggering presentation.
Good. Then